We already talked for many hours yesterday. So yesterday we already talked about the impact of AI, that AI has on healthcare, and a few challenges were mentioned. Like, for example, the discussion evolved around how it's difficult to have these old institutions in medicine and how it's difficult to integrate AI in those. And there are a lot of challenges regarding regulation and so on. So we haven't talked so much about the technical challenges. And so one technical challenge is about robustness. I think there's two examples that really illustrate this robustness challenge. The first one is the statement of Hinton in 2016, where he mentioned that radiologists will be obsolete very soon, in 5 years. And today, almost 10 years later, we have a shortage of radiologists. And so why has this happened? So the reason why this has happened is that at the time it looked like AI works extremely well for radiology. However, what the issue was it wasn't quite as robust. So it works very well in studies, but then when it comes to real life, it works significantly worse. Another example that is maybe more close to people today is ChatGPT. So people use ChatGPT and language models a lot for medical questions privately. However, there's a concern that it hallucinates. So both are technical issues regarding medicine and evolve around robustness. And so, Katharina, could you start with introducing yourself? So you're one of the researchers addressing this challenge.
Yes, thank you very much. So I'm really excited about this conversation. We've talked for basically hours yesterday already about different parts. And it's a really multifaceted problem and challenge. So as introduced, I work at the University of Würzburg as professor for pattern recognition. And what we are particularly interested in is to investigate what kind of effects do we see when we have changing environments. So for example, in hospitals, we do not have just a single vendor that, for example, provides medical devices. We do not have a standard patient in a way that always presents similarly. We have different workflows in hospitals that, of course, also impact the data that we achieve. And we have all these changes in the data also as guidelines, for example, adapt. And this is something that actually challenges the way that we, for a long time, trained and worked with machine learning algorithms. And this is, I think, a tremendous additional challenge that we see also when we talk about how can we get AI development into the clinic, because something that we would call narrow AI actually works pretty well, pretty fast, but to then get this to a state where it actually is robust and where it allows to be implemented in different situations and in different hospitals and maybe even in different countries is a long way to go, because the algorithms as we train them can be very susceptible to something that we would call confounders or shortcuts, or basically this general problem that machine learning AI solves exactly the problem that we train it to do and not necessarily the problem that we want it to solve. And this is something that we want to explore a bit more in our research and in our research group. So from a technical side, we are interested in how is something like, for example, a specific medical scanner, an MR device, a microscope, how is the signature of this scanner actually integrated in the data itself and in the networks that we train on it, and how can powerful new tools like foundation models, like basis models actually help us to address these challenges, to avoid that we have to collect data from each and every scanner, from each and every hospital, from each and every workflow, and start basically from scratch.
Oh. And that's very interesting. So one thing that you mentioned that I think is really interesting is this rise of foundation models, right? So if we think about like these first AI systems that Hinton talked about, those were not foundation models. So those were convolutional networks that were trained on labeled data. And so now we have these foundation models. So what do you think are what changes now with these foundation models? What are they, and what's the hope? How are they going to be better than those models 10 years ago?
Yeah, I think that they're a big buzzword in our community as well, like let's build foundation models and so on. And they are very powerful for data exploration, just understanding the data. Specifically in microscopy, but also in many other domains, they allow us to basically have a model that starts already somehow intelligent. So we don't need to start basically training from scratch, but we already have, I don't know, like a 10-year-old child instead of a toddler that we're trying to train. And this can be very powerful to avoid specific shortcuts that we see in the data, but it also, of course, comes with caveats. So these are then trained on potentially proprietary data. They might be underexplored for specific domains, but they are also extremely powerful to start seeing new patterns that we maybe haven't seen when we just train on a very, very narrow use case for a specific disease. So maybe in this context, like foundation models, data collection, everything around that, I think this might be something where you can contribute a little bit to the discussion. Right?
Yeah. So I'm personally very excited about the data aspect. So my research revolves around data and how we can optimize data. And so I think in the context of foundation models, like one of the first vision text foundation models was the CLIP model by OpenAI, and so it's a relatively old model, but these CLIP models are used quite frequently when it's about multimodality. And when the model came out, one thing that really was surprising to researchers, also to me, was how robust the model was. So it was much more robust to all sorts of things. It worked well on out of distribution data, and then researchers didn't really know why it was so robust, and there was research on why is it robust. And so the two ingredients were the data and the model itself, the way it was trained. And the finding after a few years of research was, well, it's mostly the data, the training data. So it seems like for these foundation models, what's really important is that you can train them on a lot of very diverse data and just a lot of data, and that just makes them very robust. And so, yeah, what I would also be curious to talk to you about is, it is very difficult so CLIP was trained on data from the internet, so cats and dogs and all sorts of pictures, but with medical data, it's not quite as easy to have all this diverse training data available, right?
So, and I think we had this discussion also yesterday, right? This access to medical data is a huge challenge, and there are currently efforts that I think all of us in the research community support to make this data easily available. And of course, lots of this has to do with the fact that there are closed medical systems. We want to make sure that our hospitals are secure, that they are not attacked. We've seen hospitals being under attack from hackers, etc. So we have these extremely secure systems on the one hand, or that we want to be secure, but we also want to have access to the data and to be able to do research with it. And all of that comes with huge infrastructure costs. And maybe in this context, what we are trying to do is to go a little bit further away from this. Let's work on the data that is kind of available in microscopy and histopathology. We're fortunate that the data is not seen as that critical in terms of privacy and so on. So there are huge databases available on the internet, like TCIA and similar repositories, where we are able to explore a lot of methodological approaches just to understand how these methods work and what kind of impact, for example, specific scanners have, specific hospitals have, and so on. But now from that, we need to go further to actually see an improvement in a clinical workflow and an improvement for a specific disease context. And for that, we need access to actually broad data sets and across Bavaria, across Germany, across Europe, to be able to train these methods.
Yeah, I fully agree. It's going to be super important to curate this data, collect all this data, and so on. But still, now if we, let's say we do this, and then we have our new foundation model, and now we use it, like a big issue is also, well, how do we know, or how does a model know that it's right or wrong? Like, so if we make a prediction, how can we trust it? Are there any methods, ideas, and what's most exciting, promising?
So probably I would take this question a little bit further, and maybe you can also add your 5 cents to that. So we we have many performance indices that sometimes work better, like worse, how many misclassifications do we have? Is a diagnosis correct from a machine learning model? Is it wrong? So percentages, looking also at subgroups is really interesting in this context of biases, of confounders, etc. Are we fair across genders? Are we fair across, or what is the performance across genders? What is the performance across different age groups and so on? So all of that we can look at. But what we see in medical imaging specifically and generally in health is that we have very, very narrow evaluations that mostly focus on a very narrow application case of AI. So for example, I have an MR image and I want to classify what kind of brain tumor this is. It's very seldom that in a clinical workflow, a decision is made just based on an MRI image, but we have this huge integration, multimodal information that comes in. And I think this also plays into the fact that we currently have this superhuman performance of AI algorithms when we do these kind of narrow evaluations. So when we try to compare like exactly the prediction from a network with exactly the prediction that a human would make on just this image without additional information, but this doesn't really reflect what is happening in the clinic. And I think there, like for researchers such as us, it will be very interesting to understand how we can combine these kinds of expertise.
That's true, yeah. I think there's also like two really interesting examples on how people address or circumvent somehow this robustness issue in practice. Like, so one is MRI imaging. So when you go have an MRI scan today in a hospital, then what happens is like this MRI machine collects measurements of your body, and then there's actually a neural network that reconstructs the image. So in a way, the image that the radiologist sees is already AI generated, if you want to phrase it like this. And so now, if you have too little data available, so if you do this scan too fast, then the method will hallucinate. And it doesn't know that it's hallucinating. And so the way how this is solved in practice is you only apply the networks in a regime where there's enough data. So in this example, there's no solution to it, but it's just like you just don't use the networks in this situation. And similar example, I think, in language models, so there's often this critique where you're going to ask ChatGPT about your medical problems, like the general public, and if it's something very common, it will get it right. If it's something maybe not so common, it can hallucinate. And so what are you going to do about this? So it's not, it's just very difficult to fix this problem. So there's one company, it's called Open Evidence. Maybe some of you have heard of it. It's essentially an LLM made for doctors, right?
Yeah.
And it does not hallucinate, and the way how they solve it is they're not training an LLM to not hallucinate. What they are doing is they're building a system that essentially looks up the things in a way. So you have a question, and then it does a search in a really big database. It gets all the relevant information, and then it makes a prediction based on that information. So it's also an interesting example, I think, because it's circumventing this robustness issue in a way, and it's not like necessarily like solving it. And it's very promising. This method, for example, gets 100% right on the American medical exam, and then humans are usually far from that. So it's pretty impressive. And so now we've talked about robustness quite a bit. Do you think there's also like other major issues, like technical issues, when using AI in the clinic or in medicine broadly?
Yeah, I think to pick up this point, this open evidence system is powerful because it directly displays where the information comes from. So we have a form of explainability basically integrated into the system. But at the same point, like this topic of explainability, interpretability is something that is pushed forward all the time. And you might have heard this yesterday in the discussion as well, that actually doctors don't look at the explanation that much. For this open evidence system, there is lots of trust that basically just this sign that there is a reference for it is enough for the explanation. Nobody is going to look in the papers unless they're really, really interested in this specific part. So I think like this topic of explainability, how do we make sure that we have a system that is transparent, but not necessarily like the typical explanations that we think about, like we have heat maps, for example, to illustrate decisions. They might not be the right way to interact with data in the medical field. So I think what will be interesting, and maybe to with a little bit of a look at the time, what we what will be a big task for us will be to understand collaboration strategies between what AI does and what humans do, because a simple collaboration is actually often not that beneficial. To understand what kind of level of transparency and explainability we need, and to kind of bring forward this idea of really benefiting, going from narrow cases where we see strong benefits of AI, so for example for triaging, for workflow management, to something that really accompanies the patient journey and allows us to integrate it into a benefit for both patients but also medical experts and hospital staff, and then everything around that in the healthcare sector.
So it seems like integration is also like a really big issue, right?
Yeah.
It's interesting how integration sometimes also changes things. So for example, with respect to breast cancer screening, right? Breast cancer screening was something 50 years ago looked very promising, but then it turned out to be very difficult to integrate it because it really changed what was discovered. It had a lot of unanticipated side effects. So maybe as we integrate AI in our workflows, there will also be such challenges that we don't anticipate. So very difficult, very interesting topic. All right, so we are at the end. So thank you very much for coming and listening.
And Reinhard, it was really fascinating. And please talk to the guys, people, right? Thank you so much.